Welcome to this brief web introduction of the UCSD Coordinated Robotics Lab, part of the Mechanical and Aerospace Engineering Department in the Jacobs School of Engineering at UC San Diego. My name is Tom Bewley, and I have the awesome job of directing the highly creative teams in both the Flow Control and the Coordinated Robotics Labs at UCSD. This talk will focus on our activities in robotics. There's a lot of buzz these days surrounding MIP, the first in a remarkable line of engaging consumer, educational, and personal robots developed in close collaboration between our Coordinated Robotics Lab at UCSD and the creative team at WowWee. MIP will come to market in May of 2014. So let's start this discussion by exploring the origins of MIP, and then take a peek at a few of the other mobile robotic systems that we are developing in the lab. We will then discuss a few of the emerging technologies that are rapidly changing the face of robotics today, and the new grand challenge applications of robotics that they enable. Finally, we will discuss briefly how these efforts impact our approach to embedded control in robotics education, both at the maker level, in high schools and beyond, and at the professional level, in universities and industry. Before I start, I want to acknowledge the talented team in the robotics lab that made everything that you're about to see happen. The lab is led by some really amazing PhD students, and every year we work with dedicated groups of undergraduates and master's students on focused research projects. At its core, the lab focuses on carefully crafted feedback control based on accurate mathematical models of a system's dynamics. To appreciate the magic of feedback, imagine first balancing a yardstick in your hand. Your eyes watching the yardstick's motion is the sensing. The movement of your hand is the actuation. Your brain, which connects the two, is the feedback. Now imagine balancing a ruler. Your brain has to respond faster because the fundamental time constant of the dynamics is now faster, because the ruler is shorter. Now imagine balancing both the yardstick and the ruler at the same time, in one hand. Stabilizing this problem is possible because the time constants of the yardstick and ruler are different, but is beyond what the human brain can accomplish. Finally, imagine also having to swing both the ruler and the yardstick up from the hanging position. This example illustrates the magic of feedback, which is this particular specialty of our lab. My own background is in the feedback control and estimation of unstable flow systems in aerodynamic applications, reducing the drag of wings and the noise from jet engines. I got my PhD in the turbulence group at Stanford, and now teach in the controls group at UCSD. On one auspicious night in 2004, before a final exam in my senior level digital controls class at UCSD, I envisaged a two-wheel vehicle that can self-upright into a Segway-like motion and, using an internal spring mechanism, hop like a pogo stick. Here are the figures from that exam. Using onboard accelerometers and gyros in addition to wheel encoders as sensors, and leveraging the wheels as both drive wheels when on the ground and as reaction wheels when airborne, the proposed vehicle can stabilize both the Segway-like motion as well as the hopping motion. Combined, these clever features enable the death-defying pit-to-fire leap shown at right. I fully anticipated that this exam would be both the birth and death of this idea. We academics are particularly good at writing down ideas that no one ever reads or follows up on. It was the remarkable energy of 3 UCSD undergraduates who approached me after this exam to tell me that they wanted to stay at UCSD for their master's degrees to build just such a vehicle that started our robotics lab. Before I start showing the actual robots developed by the folks in the lab, let me first say that, over the years, it has been the infectious generosity and team spirit of the graduate student leaders in the lab that has been the essential element of its success. A collective wisdom has developed and been shared amongst a critical mass of motivated students that have come to work together on like problems. Most of these problems are far beyond the scope and capability of a single overworked and underpaid professor. One example of this is the small motor dynamometer developed in our lab. Toy-grade motors are really quite impressive feats of engineering, given their price point when purchased in large volumes direct from the manufacturer, but they are usually poorly characterized. When developing model-based feedback controllers, an accurate model of the motor driver plus motor plus gearbox combination actually being used is essential. So one of our graduate students solved this important problem by developing a convenient and accurate small motor dynamometer, and now all of our students use it. You can use it too, as this solution is now open source. So the students in the lab are generously giving back to both the robotics community at large, as well as to their fellow lab mates. The original toy-grade self-riding mobile inverted pendulums, or MIPs as they are now called, developed in our lab were hack-stunt remote control cars with picks and sensors interconnected with custom printed circuit boards. The organic nature of the dynamics of a MIP is particularly engaging. When it stands, it gently sways back and forth, and when pushed, it takes a step back to regain its balance. In a very real way, the dynamics of a MIP mimics life. These little guys were also crazy fun to drive. Before we introduced our fun little MIPs to the toy industry, we also grappled with and solved an interesting problem. How can you reliably pick up ping pong balls with a MIP, and then energetically throw them without adding any more motors? Our initial design, shown here, left much to be desired in terms of both the reliability of the pickup and the range of the throw. Our solution to this problem, which is now patented, came from shaping the bottom of the MIP in such a way as to pinch the ping pong balls between the body of the MIP and the rotating wheel as you drive over them. The motion of the wheels then lifts the ball into the cage or pushes them up into the bottom of a hopper. We have explored a variety of launching techniques as well, while a cross-style arm is particularly effective. We also endeavored to miniaturize and robustify these toy-grade self-riding mobile inverted pendulums as the technology of microprocessors and sensors has advanced. With the help of the UCSD Intellectual Property Office, we approached the toy industry and ultimately met a kindred spirit at Huawei and went to work on the process of coming to market. Huawei took the lead on developing an iconic look for the toy. Brainstorming with a highly creative team at Huawei is in fact everything you might think it would be: fast-moving, inventive, and insanely fun. A compelling design concept soon emerged. What impressed me most as we moved to the stage of refining this design is how deliberate and methodical the process actually is. The artists at Huawei have very precise control over every curve and feature and gesture. MIP's good looks aren't just an accident of nature. In parallel with the evolution of MIP's artistic design, the UCSD and Huawei teams worked together closely on numerous design for manufacturing issues, bringing the cost of manufacturing down considerably while maintaining the extreme ruggedness and fun factor required to live up to the exacting demands of a 6-year-old. One of the key elements of this part of the effort was to streamline the internal design by putting as many components as possible on the main printed circuit board, thus enabling automatic pick-and-place machines to do the brunt of the manufacturing work. As the design matured, the Huawei team also took the lead on establishing what is known in the business as the play spec of the toy, that is, how the user can engage with it. This part of the process leveraged heavily Huawei's deep experience with both robotic toys and smartphone apps in the marketplace. A high priority at the outset of the design process was the incorporation of low-energy Bluetooth in the vehicle, not just cheap infrared, which enables highly creative engagement of the MIP with any tablet or smartphone. Boxing, dancing, path planning, stacking and carrying, everything you expect from this product, it delivers. In addition to designing the look of the toy and its play spec, Huawei took great care in the positioning of the toy in the market, from the high-tech design of its packaging to extensive engagements with all of the major toy manufacturers. To help generate additional advanced buzz, we announced MIP at the Consumer Electronics Show in Vegas, generated an active social media campaign, and provided select advanced units to charity auctions as well as to several pop stars, such as the swag bags at the Grammys, where MIP got to meet a variety of colorful public figures. Huawei is also developing print, TV, and web advertisements with various celebrities. On this front, they promised me one thing: no Justin Bieber. After this intense multi-year effort by several talented individuals on the UCSD Huawei team, we can finally invite you to meet MIP. So MIP is kind of a big deal for us. It's actually the first mass-market consumer product to emerge as a direct engagement with UC San Diego research, and it's designed to get K-12 kids excited about technology and what you can do with it. As I mentioned at the beginning of this presentation, MIP is just the first in a remarkable line of engaging consumer, educational, and personal robots developed in close collaboration between our Coordinated Robotics Lab at UCSD and the creative team at Huawei. There are many additional products from this collaboration still in the pipeline to follow MIP that I am even more excited to tell you about than MIP. Unfortunately, I can't tell you today about any of them. I'd like to shift the focus now to a few of the designs that we have been targeting over the years for more complex and serious applications than the consumer market. While many other labs in the area of mobile robotics have made impressive strides in multi-legged and biomimetic robotic vehicles, most of the work in our lab has focused on the maximum bang for the buck that you can get with wheels and treads. New ideas for enhanced maneuverability of small robotic vehicles, coupled with the rigorous design for low-cost manufacturing principles refined by the toy and consumer electronics industry, will allow us to deploy swarms of many more vehicles than we can afford to today in firefighting, search and rescue, military, and security applications. These changes will be transformative in terms of what such robots will be able to achieve in the future. Going back to the beginning of the lab in 2004, our first attempts at building a hopping vehicle, dubbed iHop, proved to be terribly crude but a necessary first step. Philosophically, in most new journeys, it's often this first step that's the hardest. As I mentioned previously, the only reason we took this step was the courage of a handful of UCSD undergraduates. This initial design incorporated springs connecting the main body to the leg going through the center of the vehicle to capture the energy of each bounce in order to sustain the hopping motion, as well as heavy wheels that serve as reaction wheels to push against with the motors when applying feedback to keep the vehicle upright. One of the key drawbacks of this prototype, besides being ridiculously heavy, was the linear slide bearings around the square leg, which would bind easily. Our design ideas, as well as our skills in both computer-aided design and physical prototyping, refined quickly. Our next design, which incorporated an elastomer spring, used a dual 4-bar linkage mechanism to achieve linear motion of the leg with rotary joints, which proved to be much more reliable. The fully extended position of the leg took the linkage mechanism just past top dead center, providing a useful locking action in a configuration enabling Segway-like motion and self-uprighting from horizontal, reminiscent of the original exam question. This design incorporates functional mass, the vehicle batteries, in both the main drive wheels as well as a third wheel mounted in the center, which was used for left-right stabilization. The design worked, but that third wheel acted something like, well, a third wheel, again making the vehicle much heavier than it needed to be. Our final hopping prototype got rid of that third wheel altogether. The patented linkage mechanism used in this design is particularly clever. It still exhibits the locking action when the leg is fully extended, enabling Segway-like motion and self-uprighting from horizontal, reminiscent of the original exam question. But it also allows a superposition of two distinct types of motion. The first with the wheels moving together, which stretches the springs in a manner that captures the energy of each bounce. And the second, with the wheels moving opposite each other, which does not stretch the springs, and may thus be used efficiently for left-right stabilization, much as a tightrope walker moves a balance bar. Though this foray into continuous hopping led to some very interesting research on novel linkage mechanisms related to the hopping problem, it proved quite difficult, at least using the technology currently at our disposal, to develop continuous hopping mechanisms that were energetically efficient when moving on Earth, as compared with wheeled locomotion. The case for hopping is much stronger in low-G environments like asteroids and moons, as a review of old videos of Apollo astronauts hopping around on our own moon quickly reveals. So we trust such a hopping design will become useful someday in the future, when the situation calls for it. We thus shifted gears in the lab and began to explore what exciting new things could be done with wheeled locomotion alone, without hopping. iHop thus gave way to Eileen, a minimalist, Segway-like design that can overcome an obstacle simply by climbing up her own leg, leaning onto the obstacle, and then self-uprighting on top of the obstacle. The original tethered prototype of the Eileen design was a bit clumsy, requiring driving via remote control and a delicate 180-degree turn on the top of each step. We are working today on an autonomous version of this design, incorporating stereo vision to detect the rise and run of each step as well as the relative vehicle position, to climb a set of stairs with a more direct end-over-end, inverse slinky type maneuver. We have partnered with ATA Engineering in San Diego to study how this design can be mechanically and thermally robustified for scouting within burning buildings with advanced sensor payloads. Our foray into the consumer market, discussed in Part 1 of this talk, focused heavily on the design for low-cost manufacturing issues that will be essential when deploying such sensor vehicles in large numbers in firefighting, search and rescue, military, and security applications. Most sphere bots are essentially remote control cars inside beach balls, as the RC car inside the sphere moves such that the center of mass of the car sphere system is not over the contact patch of the sphere with the ground. A component of the acceleration due to gravity acts to torque the system in the direction of the shifted center of mass of the system. There is a fundamental performance limitation associated with this type of actuation, due to the fact that the center of mass of the car sphere system is always inside the sphere itself. Our design, which always has the center of mass at the center of the sphere, cleverly sidesteps this fundamental limitation. Instead of actuating by shifting the center of mass, our design stores a large amount of rotational inertia by spinning up 4 heavy wheels mounted on 4 of the 6 faces of a cube, itself mounted within a sphere. By gimbaling the axes of these four spinning wheels in a coordinated fashion by the conservation of angular momentum, a very large torque may be applied rapidly to the sphere itself. As you might imagine, this system exhibits fascinating 3D dynamics and nonlinear control challenges. The missions that an energetic, internally propelled spherebot like this can perform are unique. If it is robustified, sealed, and buoyancy controlled, for instance, it can be released a half-mile off a coastline of a hostile country by a SEAL team. Leveraging its internally generated torque, it can propel itself by spinning appropriately near the ocean surface, then submerge near the surf zone to avoid being damaged by the breaking waves, and propel itself further by spinning appropriately near the ocean floor. It can then roll through the surf zone and up the beach, over sand, rocks, vegetation, barbed wire, and upstairs. No other small ground-based robotic vehicle can survive this type of mission. Spherebots have the unique property that they have no external wheels or legs to get snagged or gunked up. And this particular spherebot design has the torque available to complete maneuvers that other spherebots are fundamentally limited from performing. Moving forward with this design was one of the first instances in our lab in which a team of undergrads provide a significant force multiplier for the graduate student leading a complicated project. One of the things that particularly impresses me with talented undergraduate mechanical engineers today is their strong sense of 3D design and their ability to realize such designs accurately using CAD tools like SolidWorks. Putting together a working prototype in this configuration, with all of the necessary structural and functional members, was essentially like designing and building a tightly constrained 3D jigsaw puzzle. Undergraduate mechanical engineers joined forces with a graduate student lead on this project to solve this problem effectively. Switchblade is an agile treaded robot design. The treads provide excellent traction over a variety of terrain, including vegetation, gravel, sand, and mud. Switchblade has a unique patent-pending feature. Each tread assembly can pivot relative to the central chassis. This can be used to shift the center of mass of the vehicle to climb over obstacles. Using feedback similar to that implemented in a MIB, Switchblade can also stand up and balance on either the distal or proximal ends of its treads, thereby extending its stature significantly and allowing it to overcome obstacles that are large relative to its own size. This facilitates a successive perching maneuver, as indicated in the subfigure at right, that allows Switchblade to climb stairs by balancing on the edge of one step at a time, while keeping the treads at a relatively constant angle, and moving the angle of the body back and forth to keep the center of mass over the contact point with the step at all times. This allows us to build a treaded vehicle that is much smaller and cheaper than the Packbot and Talon vehicles fielded by the militaries today, but is still able to negotiate easily standard human-sized steps and stairs. We have deployed Switchblades with appropriate advanced sensor packs in a number of interesting scientific experiments, one of which, related to plume estimation and forecasting, will be discussed later in this talk. An undergraduate team worked with a graduate student lead on this project to build up a fleet of a dozen Switchblades, half of which we gave to National Instruments, who sponsored us on this project, to promote the NISB Rio board about which the Switchblade was built. Using the design for low-cost manufacturing principles explored in the manufacturing of MIP, we also prototyped how the Switchblade design can be miniaturized to shirt pocket scale, while retaining the full range of motion of the original Switchblade prototype. Creative explorations like this keep our conversations with our friends in the toy industry quite active. Here's an interesting new design leveraging dynamics and feedback in a clever way for moving along cables and ropes. This design has a single strong motor at the elbow and a pair of carefully designed 3-position clamps that can either grab the cable, roll along the cable, or release from the cable as necessary. This range of motion enables the vehicle to move along a cable like a child swings on a set of monkey bars, which in turn can be used to swing past cable support points. We have also considered the problem of climbing and negotiating air conditioning ducts in underground tunnels. The design we have converged upon is inspired by the remarkable principles of tensegrity structures, that is, structures built from tendons and bars under pure tension and pure compression that can be pre-tensioned and optimized for a wide variety of possible loading and actuation scenarios. Our design consists of 2 nested tetrahedral structures interconnected by 4 vertical tendons and 4 saddle tendons. The top bar of the upper tetrahedron and the bottom bar of the lower tetrahedron are linear actuators that can be used to wedge between the walls of a duct, or to release from the wedged positions. All of the batteries, motors, and electronics used to drive the structure are embedded and protected within its bars. To climb a duct, the lower tetrahedron is wedged in place, and the saddle tendons are shortened, lifting the upper tetrahedron. Then the top tetrahedron is wedged in place, and the vertical tendons are shortened, lifting the lower tetrahedron, thereby entering an inchworm-type motion to climb the duct. Remarkably, this dual-nested tetrahedral assembly also serves as a powerful high-degree-of-freedom joint. When one of the tetrahedrons is held in place, the 8 tendons may be actuated in such a way as to steer the other tetrahedron over a wide range of controllable motions, allowing the robot to turn corners at junctions of the duct in a controlled fashion. Most robotic arms today are built with long and heavy cascades of single degree of freedom joints, with many structural members suffering from significant bending loads. We believe that, leveraging such tensegrity principles, there is significant utility in exploring the use of high degree of freedom joints of this sort for applications in advanced robotic arms, in addition to serving as the essential foundation for duct climbing robots. Given the many remarkable properties of controllable tensegrity structures, industry has been relatively slow to apply them. One of the possible reasons for this is the technical difficulty of building quality tensegrity structures equipped with both sensors and actuators, with robust joints that are faithful to the pin joints of the tensegrity ideal. Our team has invested significant time pushing the state-of-the-art in the technical challenges of such builds. In the example shown here, we have the motors driving the tendons of the tensegrity structure embedded within the bars of the tensegrity structure and mounted on small arms made of springy 7075 aluminum outfitted with strain gauges. The resulting force and direction of each tendon may then be deduced reliably from the strain gauges instrumenting each motor mount. I would like to focus now more specifically on how the area of robotic design is changing rapidly due to emerging technologies. Though fun to drive, the ball handling skills of our original mobile inverted pendulum prototypes discussed earlier were quite poor. These prototypes actually sat in what we dubbed the drawer of shame for a couple of years, as various students failed to find good solutions for reliable ball pickup and for energetic throws. This interesting problem was eventually solved by a young master's student with a keen sense of 3D thinking and the ability to implement this vision in CAD, coupled with the emergence of 3D printing. This is truly a problem that we couldn't solve before 3D printing was readily available to us. As I mentioned previously, our solution to this problem came from carefully shaping the bottom of the MIP in such a way as to pinch the ping-pong balls between the body of the MIP and the rotating wheels as you drive over them. The motion of the wheels then lifts the ball into the cage or pushes them up into the bottom of a hopper. As a side note, another really fun part of this job is when we can show off such cool ideas from the lab to the luminaries in robotics today, in this case Dean Kamen. Another thing that characterizes the field of mobile robotics today is the explosion of microprocessors that are available to be used, which is both an amazing blessing in terms of the remarkable flexibility it provides, and also something of a curse in terms of keeping up with all of the rapidly changing options. Our team has focused on the microprocessor families shown here. Our work in this area began with PICs, which have mostly been supplanted by Arduinos once they became available. For production purposes, like in MIP, a fast 32-bit ARM Cortex-M0 is about 80 cents a piece when purchased in quantity. 80 cents is a wholly remarkable price point for such advanced technology, and indicates how far this industry has come. Arduinos are quite easy to use when prototyping, and in some targeted situations are exactly what the application calls for. Indeed, due to their ease of use, Arduinos are causing something of a revolution in the maker movement in high schools and beyond. However, the Arduino sketch environment unnecessarily limits users to an essentially single-threaded mindset. In modern robotics applications, one invariably needs to work on many problems at once, with different loop rates and different priorities. Such a setting is greatly empowered by small Linux computers, such as the powerful FPGA and LabVIEW-equipped offerings from National Instruments, the amazing $45 credit card-sized BeagleBone Black, and the Snapdragon-powered offerings from Brain Corporation and Qualcomm. This last board, still under development at Qualcomm and publicly announced in December of 2013, is about 1 inch square, runs at about 1 watt, and is 10 times more powerful than the fastest supercomputer in the world in 1985. Imagine the useful problems that could be solved if we started doing more with such processors than playing Angry Birds. The related problems of SLAM, or simultaneous localization and mapping, and SFM, or structure from motion, were introduced by a 1980s computer game called Rogue. In this game, you controlled the motion of a character through an unknown environment, searching for objects while avoiding dangers. A 2D map of everything your character had seen thus far was generated as the game evolved, so you could explore its passageways and retrace your steps back out. Shortly after the game of Rogue was introduced, an artificial intelligence learning algorithm called Rogomatic was developed in order to play the game of Rogue autonomously. Rogomatic was thus the genesis of modern attempts at SLAM, which is the same problem with a character replaced by a real robotic vehicle moving through a real environment. SFM algorithms, in contrast, focused on generating a realistic 3D virtual reality of an environment based on 2D image sequences from a robot and, often, information about how the robot itself is moving. Recent active research efforts around the world focus on solving the SLAM and SFM problems collaboratively, combining the information being collected from several independent vehicles moving in real time. With modern cell phone technology and massive software efforts such as Google's Project Tango, Qualcomm's FastCV and Vuforia projects, and various crowd-funded efforts such as Occipital's Structure Sensor, the problems of SLAM and SFM are quickly becoming mature. Our collaborators at UCSD are focused on the use of advanced artificial intelligence techniques to further accelerate the algorithms at the heart of these difficult problems. Advanced SLAM and SFM capabilities are an essential game changer for the useful missions that squads of inexpensive robotic systems moving through unknown and dangerous environments can perform. Our lab has focused in particular on the use of inexpensive infrared thermal imaging systems from DRS technologies to augment the 3D virtual realities developed by our small wheeled vehicles as they move around smoke-obscured environments. The information gained in the infrared spectrum is compelling and relevant, as it quickly points out certain fire dangers, as well as warm bodies, in the environment. Of course, there are many more advanced technologies and systems than we can possibly cover here, including commercial off-the-shelf unmanned vehicles, secure low-power long-range communication technology, and amazing high-performance computing capabilities in the proverbial cloud. Emerging technologies of these sorts enable a host of new applications. A particularly compelling overarching application for many subproblems in coordinated robotics today is the problem of the estimation and forecasting of contaminant plumes in the environment, such as the ash from a large volcano in Iceland, the oil from the Deepwater Horizon, the radiation released from the Fukushima nuclear power plant, and preparing for the possibility of an airborne chimrad bio-release in a major U.S. city, and how to rapidly coordinate an evacuation in the face of such an event to save the maximum number of lives. The problem of forecasting the spread of wildfires threatening urban areas is similar. In such grand challenge problems, remote sensing from satellites is certainly valuable, but often gives an incomplete picture. Coordinated fleets of unmanned sensor vehicles that can probe the domain of interest are often essential for addressing the relevant uncertainties of how such systems are evolving. It has become painfully evident in recent years, through our bumbled response to certain events like those depicted here, that our current capabilities for this class of problem leave significant room for improvement. Our lab has developed some rigorous and numerically tractable new algorithms to address such problems, and has performed some initial proof-of-concept studies showing how these algorithms might be deployed using a fleet of sensor vehicles in small-scale theater smoke experiments in a remote parking lot near UCSD. Precise description of the algorithms developed and tested are beyond the scope of this introduction, but I would like to spend a bit of time talking about our experiment, which shows how it all comes together. The theater smoke used in this experiment was heavy and mostly stayed near the ground, which lent itself well to essentially 2D simulations to model, approximately, the evolution of the smoke plume. More general problems will certainly require 3D simulations as well as 3D sampling of the environment. Note, however, that most environmental flow systems are quite stably stratified, with minimum mixing between layers, so plumes are often much more 2D than one might first imagine. The winds and smoke in this experiment were monitored by commercial off-the-shelf sonic anemometers and particle sensors mounted on each sensor vehicle. An eye-in-the-sky view was provided by a weather balloon and camera for post-processing after the experiment was concluded. One of these white dots is Chris. The rest are the sensor vehicles moving around in the vicinity of the smoke plume. Once a second, each sensor vehicle transmitted a small packet of measured information over an ad hoc Wi-Fi network set up over the parking lot, including wind intensity and direction, smoke density, time, and GPS location. As the experiment evolved, there were two major weather forecasting class problems that needed to be solved in real time. The first problem to be solved, based on the available measurements of the flow state in the recent past, was to estimate both the smoke distribution and the wind distribution driving its evolution near the ground plane, while also characterizing accurately the uncertainty of this estimate. This problem is known as state estimation or data assimilation. The second problem to be solved, looking over various projections into the near future, was to optimize feasible trajectories of the dozen sensor vehicles in a model predictive control fashion in order to minimize a quantitative measure of the uncertainty of the forecast at some time in the near future. This problem is known as adaptive observation. Both the state estimation and the adaptive observation problem were of the computational grand challenge variety, and were thus solved in real time on a massive NSF supercomputer cluster off-site. A key point is that the bandwidth required to use the dozen sensor vehicles effectively in this rapidly evolving, centrally controlled problem was very small indeed. A single 3G cell phone was enough to keep all of the data packets streaming from the sensor vehicles, through the network set up in the parking lot, back to the cluster solving the weather forecasting class problems in real time, as well as to keep frequent updates of a handful of waypoints streaming back out to each sensor vehicle, also in real time, in order to keep each vehicle headed in the directions of maximum utility for the weather forecasting problems at hand. Note that the control algorithm guiding each vehicle did not naively simply seek the extremes of the smoke density, nor simply orbit along the contours of constant smoke density. Instead, the control algorithm was designed rigorously to minimize a quantity, the trace of a covariance matrix, measuring the uncertainty of the location of the smoke plume at the forecast time, which is a precise statement of what the sensor vehicles were deployed for in the first place. How the vehicles move in this experiment is thus precisely targeted, though it might at first appear somewhat non-intuitive, as the vehicles are being dispatched mainly to estimate the winds with maximal accuracy, not to dive into the plume itself. Once the source location and the winds driving the plume evolution are known accurately, the time evolution of the plume itself follows in a highly predictable fashion. Here is a computational experiment illustrating the simultaneous execution of the state estimation and adaptive observation problems. The figure in the upper left is the truth model, indicating the winds and the smoke density. Information was transmitted from this truth model to the supercomputer cluster solving the state estimation and adaptive observation problems only at the sensor vehicles, indicated by the black dots. The figure in the lower left is the ensemble mean, indicating the real-time estimate of the fluid state, and the smaller figures at right indicate the ensemble variance, indicating the current uncertainty of the distributions of the two components of the velocity and the smoke. The tracks in the lower right subfigure indicate the optimized waypoints sent out to each sensor vehicle, and frequently updated, by the adaptive observation algorithm. In the receding horizon model predictive control framework, the vehicles each travel to their first waypoint, by which time the remaining waypoints are updated and extended. Note that, after a short period of time, the estimate synchronizes accurately with the truth model. Note also that it is fashionable in the controls community these days to focus primarily on decentralized vehicle coordination algorithms. A key point that this experiment makes clear is that there is plenty of interesting and relevant work to be done using centralized algorithms to coordinate the motion of sensor vehicles, together with high-performance computing resources running weather forecasting class, state estimation, and adaptive observation algorithms in real time. In problems of this scale, it is natural to stay in radio contact with the sensor vehicles, which are often somewhat expensive. It is therefore logical to solve the challenging state estimation and adaptive observation problems centrally using the most powerful computers that you have at your disposal. At any point that a forecast is needed, of course, the current state estimate in this data assimilation algorithm, which is being run in real time, is simply march forward the specified amount of time into the future. In order to introduce the key elements of robotics to today's students, who will ultimately be responsible for carrying this revolution in robotics and its applications into the future, our lab is hard at work developing new educational resources. In 2012, our lab began offering a new embedded control and robotics course in which, starting with a bag of parts, each individual student built and controlled his or her own small and mobile inverted pendulum from scratch. The assembled vehicles included a breadboard mounted to laser cut and 3D printed parts, to which the students wired up a Bluetooth module, an Arduino Nano, H-bridges to drive the motors, and cell phone-grade accelerometers and gyros to sense the vehicle orientation, in addition to the all-important BLIFNARs, that is, blinking lights for no apparent reason. On the end of each motor, each student hand-built an optical quadrature encoder and learned how it functioned from the ground up. The students then programmed the Arduino with classical single-input, single-output control techniques implemented in discrete time in a successive loop closure framework, with an inner loop controlling the vehicle orientation and an outer loop controlling the vehicle speed. We refined this course significantly in 2013, ditching the Arduino Nano in favor of a Texas Instruments $45 credit card-sized Linux computer known as the BeagleBone Black. The students also used a new general-purpose high-performance robotics connector board, or CAPE, designed by our lab for applying the BeagleBone Black in robotics applications, and got to take a peek at how this connector board was meticulously designed and precisely specified for off-site fabrication using Eagle. The students again learned about the fundamental issues of controlling motors, including quadrature encoders, H-bridges, and pulse width modulation, in addition to communication over the I2C and SPI buses. The result this year was a significantly more refined experience, targeting the manner in which prototype robotic systems will be developed in the future for two specific reasons. First, the vehicle is Linux-based, not Arduino-based. As I mentioned previously, the Arduino sketch environment unnecessarily limits the user to an essentially single-threaded mindset. In modern robotics applications, one invariably needs to work on many problems at once, with different loop rates and different priorities. Such a setting is greatly empowered by small Linux computers such as the inexpensive BeagleBone Black. Second, in the age of easy and fast turnaround of custom mail-ordered printed circuit boards, there is no longer any reason to use large clumsy breadboards, even in prototype robotic systems. Custom printed circuit boards are, of course, much more reliable than breadboards in mobile robotic systems. Given that they are now so easy and inexpensive to design and fabricate, custom PCBs should now be leveraged broadly by the robotics professionals and makers alike. With this new Linux-based educational paradigm now essentially worked out, we are currently working with our partners at Texas Instruments and Huawei to make it broadly available through SparkFun, MakerShop, and elsewhere. We are targeting 3 core systems around the BeagleBone Black and our general-purpose CAPE. The curriculum starts with a dynamically stable but kinematically interesting rover with extreme 4-wheel steering, which enables 90-degree translation of a 4-wheel vehicle for parallel parking in extremely tight spaces. Students move on to dynamically stable but fast-moving quad rotors, where they study remote control and waypoint navigation in 3 dimensions. Finally, they graduate to a dynamically unstable mobile inverted pendulum that they build and control from scratch. All of this is done in an industry-standard Linux environment, empowering the student with a very general set of tools once all 3 systems have been built and mastered. The curriculum, which we hope to make available as a massively open online course, or MOOC, in due course, targets two specific markets: the maker market in high schools and beyond, where students are beginning the process of connecting their physical and digital worlds, and the professional market in universities and beyond, where students are developing advanced and embedded controllers using new technologies for emerging applications that have not previously been viable. The changes in technology that are empowering this current revolution in robotics and its applications are nothing short of remarkable. The first and second derivatives of these changes are positive, and will be for the foreseeable future. Educational materials are emerging that make it easier than ever for you and your kids to get involved. And those involved will help shape how robotics will change the future of our planet, hopefully so we can take better care of each other, leaving machines to do the jobs that are boring, dirty, repetitive, remote, or dangerous. I hope this presentation has helped to provide you the inspiration to get involved.